Greetings, everybody. Learning is a hobby here. I wanted to go over my summary for section 4.1 in Terence Tao's book, Analysis 1. So that's what I'm going to do here. Let's jump into it. We're finally into constructing the integers, which is what this section is about. So here's my summary. We start, of course, with the definition of the integers. So actually, let me just move some things out of the way here on my screen. Okay, so definition 4.1.1 says an integer is an expression. I'll talk about that star in a second. An integer is an expression of the form a minus minus b, where a and b are natural numbers. Two integers are considered to be equal. Minus minus b equals c minus minus d. If and only if a plus d equals c plus b, we let that symbol z denote the set of integers, which you're probably familiar with. So he has a note here, which is why I put a star by the word expression. He says, in the language of set theory, what we're doing is starting with the Cartesian product of the natural numbers with itself and defining a minus minus b as an equivalence class under the equivalence relation. A comma b is equivalent to c comma d if and only if a plus d equals c plus b. In other words, a minus minus b is the equivalence class of ordered pairs in the Cartesian product N2, where a comma b is equivalent to c comma d, referring to that relation. The existence of the set Z, which is the set of all those equivalence classes, then follows from two applications of the axiom of replacement. He says, though, however, this interpretation plays no role in how we manipulate the integers and will not be mentioned again. A similar set theoretic interpretation can be given to the construction of the rationals and the real numbers. We'll see those later on. So in the next section, actually, he will construct the rationals, and in the next chapter, we'll construct the reals in Tau. And also remember, we're going to construct the reals in a different way in Spivak's book. Okay. He says here also, we need to verify that this definition satisfies the axioms of equality from section A7, which is the appendix. Substitution, however, must wait until we define operations on the integers, but we can verify reflexivity, symmetry, and transitivity now. So here's proposition. He actually proves transitivity in the book, and he leaves reflexivity and symmetry for an exercise, but I just did them here because they're short, and I figured why not just do them here instead of waiting for the exercise set. So the proposition is the above relation is reflexive, symmetric, and transitive. So here's the proofs. We'll start with reflexivity. So obviously a plus b is equal to a plus b, which means that a minus minus b is equal to a minus minus b. Then symmetry, let a minus minus b equals c minus minus d, then a plus d equals c plus b, implies d plus a equals b plus c. That's from commutativity of addition of natural numbers. And that implies that c minus minus d is the same equivalence class as a minus minus b. All right, and then transitivity as well. Like I said, he actually proves transitivity in the chapter, so this is his proof. Let a minus minus b equal c minus minus d, and c minus minus d equal e minus minus f. Then a plus d equals c plus b, and c plus f equals e plus d by definition. And that implies that a plus d plus c plus f equals c plus b plus e plus d. In other words, I'm just adding those two equations together, which implies a plus f equals e plus b by cancellation, which is property cancellation here we're talking about inside the natural numbers. That's proposition 2.2.6, sorry, 2.2.6 from chapter 2. Therefore, a minus minus b equals e minus minus f. Okay, and we're going to have to wait for substitution for when we define addition and so on, which we're going to do right now. Definition 4.1.2, the sum of two integers, a minus minus b plus c minus minus d, is defined by the formula a minus minus b plus c minus minus d is equal to a plus c minus minus b plus d, and the product is defined in the way that you would think it would. The product of two integers, a minus minus b times c minus minus d, is defined by a minus minus b times c minus minus d is ac plus bd minus minus ad plus bc. It's kind of, just think about like distributing, right, over when you're multiplying two binomials together. And then after the definition here, he has a lemma, which is that addition and multiplication are well defined. So substitution, we're going to verify here. Let A, B, A prime, B prime, C, D be natural numbers. If A minus minus B equals A prime minus B prime, then A minus minus B plus C minus minus D is equal to A prime minus minus B prime plus C minus minus D, and A minus minus B times C minus minus D equals A prime minus minus B prime times C minus minus D. And also the other, addition is commutative as well, in other words. So addition and multiplication, it doesn't matter what side you multiply or add on. Thus, addition and multiplication are well-defined operations. In other words, equal inputs give equal outputs. So here's the proof. So part one, I'll start with addition. Let A minus minus B equal A prime minus minus B prime. Then A plus B prime equals A prime plus B. Then consider A minus minus B plus C minus minus D. By definition, that's equal to A plus C minus minus B plus D. And A prime minus minus B prime plus C minus minus D is equal to A prime plus C minus minus B prime plus D, again, by definition. Then A plus C plus B prime plus D, you can rewrite over as A plus B prime plus C plus D, which is equal to A prime plus B plus C plus D, which is equal to A prime plus C plus B plus D. That implies that A minus minus B plus C minus minus D equals A prime minus minus B prime plus C plus D. And also C plus A plus D plus B prime is equal to C plus A prime plus B plus D by proposition 2.2.4, which implies that C plus A minus minus B plus D equals C plus A prime minus minus D plus B prime, which implies C minus minus D plus A minus minus B equals C minus minus D plus A prime minus minus B prime. All right, so that verifies well-definedness for addition, and I won't go through the whole process but it's a similar thing for multiplication. You could read it here, so you don't have to hear me say minus a million times again. So here you can look at the proof for that. He says after that, note, if n is a natural number, we can identify n with n minus minus 0 in Z. We can do this because there is an isomorphism from the natural numbers to the integers. If we let n be equal to n minus the equivalence class n minus minus 0, then all definitions of addition, multiplication, and equality are still valid since they are consistent. For example, n plus m is equal to n minus minus 0 plus m minus minus 0, which is n plus m minus minus 0. And similar thing for multiplication. Furthermore, 0 is the equivalence class 0 minus minus 0, and 1 is the equivalence class 1 minus minus 0, etc. Also, incrementation for x in Z also carries over. In other words, the successor of x is defined to be equal to x plus 1. This operation, however, is no longer important to us because it's been superseded by the more general notion of addition. Okay, we also next define another operation called negation of integers. So a minus minus b is an integer. If a minus minus b is an integer, we define the negation minus a minus minus b to be the integer b minus minus a. In particular, if n is equal to n minus minus 0 is a positive natural number, we can define its negation negative n to be the equivalence class 0 minus minus n. All right. Then we also show that that operation is well defined, which I do down here. Here's my proof. Let a, b, a prime, b prime be natural numbers. Let a minus minus b equal a prime minus minus b prime. Then a plus b prime equals a prime plus b. Then b plus a prime equals b prime plus a, which implies b minus minus a equals b prime minus minus a prime, which implies that negative a minus minus b is equal to negative a prime minus minus b prime. Right, so negation is well defined. Right, next we have a trichotomy lemma for the integers. So lemma 4.1.5, let x be an integer, then exactly one of the following three statements is true. A, x is 0, B, x is equal to a positive natural number n, or C, x is the negation negative n of a positive natural number n. So here's my proof. Let x be an integer, then there are a, b, and n, such that x is a minus b. Then a equals b, a greater than b, or a minus b by trichotomy of natural numbers, right? A, b, and c are, sorry, just a and b. A and b are natural numbers. So natural numbers has, satisfies trichotomy. So let's take a look at number one. If a, we'll do, the three cases here. If a equals b, then x equals a minus a, which is equal to the equivalence class 0 minus 0, since a plus 0 equals a plus 0. That implies that x is 0. Okay, case two, if a is greater than b, then there is a c in the natural numbers, such that a is b plus c, then x equals a minus b equals b plus c minus b, which is b minus b plus c minus 0, which is equal to c minus 0, because b minus 0 is the equivalence class 0 minus 0, right? Then case three, if b is greater than a, then b equals a plus c for some c in the natural numbers. Then x is a minus b equals a minus a plus c, which is equal to a minus a plus 0 minus c, which is equal to 0 minus c, because a minus a again is in the equivalence class of 0 minus 0, which implies that that's equal to negative c minus 0. All right, and then we just have to show that only exactly one of those can happen. So not more than one of those can happen at the same time. So also a and b can't happen simultaneously, since if 0 minus 0 equals n minus 0, that implies that 0 plus 0 is n plus 0, which implies that n is 0, which contradicts that n is positive, or sorry, n is greater than 0. Or in other words, n is a positive natural number. Oops, I hope I didn't sit on the volume. Okay. Also, a and c can't happen simultaneously, since 0 minus 0 equals 0 minus n implies 0 plus n equals 0 plus 0, which implies n equals 0, which again contradicts that n is non-zero natural number. Finally, b and c can't happen simultaneously, since n minus 0 equals 0 minus m implies n plus m equals 0 plus 0, which is 0, which contradicts proposition 2.2.8. Therefore, exactly one of a, b, c must be true. All right, so that shows trichotomy for the integers. There's a note here. While we could have taken lemma 4.1.5 as a definition for the integers, this would make defining operations on z much more complicated, since we would have to consider many cases. For example, positive times negative is negative, negative times negative is positive, et cetera, right? And similar thing for addition. Negative plus positive can either be negative, 0, or positive, depending on which has the bigger magnitude. And so there's a bunch of cases, which means that the definition of the operations would be a lot messier than the way that we defined them. So, all right, proposition 4.1.6, the laws of algebra for integers. Let x, y, z be integers. Then we have, so there's a bunch of rules. Addition is commutative. Addition is associative. There's an additive identity. There are additive inverses for each integer. Multiplication is commutative, multiplication is associative. There's a multiplicative identity for every integer. And then multiplication distributes over addition. All right, and the proof is left for an exercise, so we'll do that in the exercise set. There's a remark here, however, remark 4.1.7, he labels it, the above 9 identities assert that Z forms a commutative ring with identity. If you remove the property that multiplication is commutative, then you just get that Z is a ring. But Z is not just a ring; it's a commutative ring, because multiplication of integers is commutative. All right, we can now define the operation of subtraction x minus y of two integers by this formula here: x minus y equals x plus minus y. So here we're defining subtraction in terms of addition of negatives. Right, we don't need to verify that this operation is well defined, since we've already showed that addition and negation are well defined, and we're defining subtraction in terms of those two things. Right, then if AB is a natural number, A minus B equals A plus minus B equals A minus minus 0 plus 0 minus minus B equals A minus minus B. So A minus minus B is the same thing as A minus B, and we can now discard that annoying minus minus notation and use the familiar subtraction symbol. Okay, proposition 4.1.8. Integers have no zero divisors. Let A and B be integers such that A times B is 0. Then either A is 0 or B is 0 or both. He leaves the proof for an exercise, so we'll deal with that in the next video. Corollary 4.1.9, cancellation law for the integers. If A, B, C are integers such that AC equals BC and C is non-zero, then A equals B. And again, he leaves that for us to do in the exercise set, the proof, I mean. Right, almost to the end of the section, actually. Definition 4.1.10, ordering of the integers. Let n and m be integers. We say that n is greater than or equal to m, and write n, greater than or equal to m, or m less than or equal to n, if and only if we have n equals m plus a for some natural number a. We say that n is strictly greater than m, and write n greater than m, or m less than m, if and only if n is greater than or equal to m, and n is not equal to m. So this is almost word for word the same definition of ordering of the natural numbers. So everything carries over, unchanged from this to the natural numbers and vice versa, right? So nothing is changed by this. All right, last thing, lemma 4.1.11, properties of order. We're going to prove this in the exercise set as well, but there's a bunch of properties here. Let A, B, C be integers. Okay, part A, if A is greater than B, A is greater than B if and only if A minus B is a positive natural number. B, addition preserves order. If A is greater than B, then A plus C is greater than B plus C. Part C, positive multiplication preserves order. If A is greater than B and C is positive, then A times C is greater than B times C. Negation reverses order. If A is greater than B, then minus A is less than minus B. Part E, order is transitive. If A is greater than B and B is greater than C, then A is greater than C. And finally, order trichotomy, which we've actually already talked about. Exactly one of the statements, A greater than B, A less than B, or A equals B is true. And again, he leaves the proof here to the exercise set for us to do, which we'll do in the next video. So kind of a short section, but we have a bunch of propositions that we have to prove in the exercise set. So let me stop my screen share. So that's section 4.1, the summary for section 4.1. There's a lot more stuff that he talks that he, a lot more stuff that he says in section 4.1. So, I always sort of like whittle everything down to just the bare bones. So it's worth, it's always worth reading the section itself. But, I have all the important stuff written out there in my summary. So I'll see you guys in the next video, which should be the exercise set for section 4.1. I should be able to get that done by tomorrow, actually, because it's not too long of a exercise set. There's just a bunch of theorems and stuff that we have to prove. So I'll see you in that one, and let me know what you guys think down below, and I'll see you next time.